Welcome to the Eternon channel. This is a place for gentle science-based stories about Earth and its past, created for learning relaxation and sleep. If you find it helpful, please like and subscribe to support the channel. Now take a breath and begin.
The Milky Way is not still. On the largest scales, stars, gas and dust move in broad-ordered flows shaped by gravity and time. The galaxy rotates, carrying its contents around a shared center over hundreds of millions of years. Within this rotation, smaller motions layer themselves quietly. Stars drift relative to one another. Clouds stretch and thin. Debris released from planetary systems joins the general circulation, becoming part of a diffuse interstellar population. This background motion defines what is expected of any object not bound to a single star. It sets the reference frame against which unusual behavior is judged. In this outermost region, nothing about movement is personal or dramatic. Everything follows from mass distance and accumulated gravitational influence. An interstellar object begins its story here not at detection, but embedded in this slow, persistent flow. Typical velocities relative to the Sun fall within a known range shaped by the Sun's own motion through the galaxy. Objects approach from many directions, but their speeds cluster around values set by galactic dynamics, rather than local chance. This creates a baseline. When a new object is detected, its motion is first compared to this baseline not to human expectation, but to the quiet statistics of the Milky Way itself. The Sun moves relative to nearby stars at a steady pace. Interstellar objects encountered near the solar system tend to reflect this motion. Their inbound speeds, when corrected for solar gravity, usually align with what is expected from random sampling of the local stellar neighborhood. This does not mean their paths are simple. Each object's trajectory is unique, shaped by past encounters that are no longer traceable in detail. However, when many such paths are considered together, patterns emerge. These patterns are stable. They form the background against which deviation becomes visible. In this context, the outer environment is defined not by emptiness, but by regularity. Even the apparent randomness of interstellar space has structure. Density is low but not zero. Radiation fills the void. Magnetic fields thread through plasma. Small particles drift, collide, and separate again. Over long durations, these conditions impose gentle but cumulative effects. They do not push objects abruptly. They guide them gradually. Any object surviving long enough to reach the solar system has already demonstrated compatibility with this environment. It has not been torn apart by tidal forces. It has not been eroded into dust by radiation alone. It has persisted through millions or billions of years of travel. This persistence is assumed at the outset. It is not remarkable. It is simply necessary. When observers first notice a fast-moving point of light against distant stars, the initial step is to situate it within this galactic context. The motion is measured. The path is projected backward and forward under gravity alone. At this stage, no claims are made. The object is treated as a test particle moving through a known potential. If its behavior fits within the expected distribution, attention remains routine. If it does not, the difference is noted carefully. The difference must be established relative to the baseline, not relative to surprise. In the outermost region of analysis, there is no anomaly, only comparison. The galaxy provides the scale. The object provides the data. For 3I/Atlas, this comparison begins with velocity. Its speed relative to the Sun is measured as it approaches. After correcting for the Sun's gravity, the remaining velocity is compared to the expected range for interstellar debris. This range is not narrow, but it is bounded. The initial measurements place the objects near the center of this distribution. It is neither unusually slow nor unusually fast. Direction is also considered. The approach vector does not align with any known stellar stream in a way that would be improbable. It arrives from a direction populated by many stars, not from a void. At this level, the object behaves as expected. There is no signal here that demands explanation beyond standard galactic motion. The background also includes time. The solar system moves through different regions of the galaxy over long intervals. The density of interstellar debris encountered may vary slightly with location, but not dramatically. The present epoch is not unique. Objects like this could have passed before and will pass again. Detection depends on surveys, not on cosmic timing. This is important. The outer context does not single out the object as special. It treats it as one sample drawn from a continuous process. This restraint is deliberate. The narrative does not begin with deviation. It begins with fit. The fit establishes trust in the framework. Only after the framework holds can deviation be identified without confusion. The outer region also includes the expectations built from prior detections. 2 interstellar objects have already been identified passing through the solar system. Their motions, while distinct, fall within the same broad galactic patterns. They provide reference points, not templates. Each new object is not compared to them directly, but all are compared to the same background. This avoids false contrast. It ensures that differences are measured against physics, not against memory. In this way, the outermost layer of analysis remains calm and impersonal. It asks only whether the object belongs to the general flow of the galaxy. For 3I/Atlas, the answer at this stage is simple. It does. Nothing about its initial motion violates the expectations set by galactic dynamics. Nothing demands immediate revision of models. This does not diminish interest. It grounds it. By confirming that the object shares the same outer context as countless unseen interstellar bodies, the analysis secures a stable starting point. From here, the focus can move inward toward more local conditions without carrying uncertainty from the larger scale. The galaxy has done its part. It has provided a reference. Within that reference, the object is placed quietly and without emphasis, ready for closer examination. Within the broad galactic flow, individual interstellar visitors form a sparse and uneven population. They are not evenly distributed in size, composition, or history, but they do share certain broad characteristics shaped by the environments they leave and the journeys they endure. To understand what is typical, observers do not rely on a single example. They draw from models of planetary system formation, from observations of debris disks around other stars, and from the small number of confirmed interstellar objects already detected. These sources together define expectations, not rules. Interstellar visitors are understood as fragments. They are byproducts of processes that operate around stars, not primary bodies formed in isolation. Planets form within disks of gas and dust. Smaller bodies grow alongside them. Gravitational interactions scatter some of this material outward. Over time, close encounters with giant planets or passing stars eject debris into interstellar space. This mechanism is well supported by simulations and by the structure of planetary systems observed elsewhere. It implies that most interstellar objects originate in environments where heating collisions and chemical processing have already occurred. They are not pristine. They carry histories shaped by stellar radiation and planetary gravity before ejection. Typical expectations follow from this origin. Many interstellar objects are predicted to be small because smaller bodies are more easily ejected. Larger bodies tend to remain bound unless disturbed by strong interactions. This suggests a population dominated by objects ranging from tens to hundreds of meters, with larger ones being rarer. Composition is expected to vary. Objects ejected from inner regions of planetary systems may be rocky or metal-rich. Those from outer regions may retain ices and volatile compounds. However, long exposure to interstellar radiation alters surfaces regardless of origin. Volatiles near the surface are lost over time. Radiation darkens and chemically modifies exposed layers. As a result, many interstellar visitors are expected to appear dark and spectrally neutral when observed from afar. Activity such as outgassing is possible but not guaranteed. It depends on size, composition, and thermal history. Prior detections provide limited but valuable context. One object showed no obvious activity despite passing close to the Sun. Another displayed comet-like behavior with gas release. These differences are not contradictions. They reflect diversity within a shared framework. Neither case requires new physics. Both fit within existing understanding of small body behavior under varying conditions. From these examples, observers learn caution. One object cannot define the class. Each detection adds a point, not a pattern. Typical behavior must be inferred statistically, not narratively. This approach shapes how new objects are evaluated. Expectations are broad by design. When 3I/Atlas enters consideration, it is placed within this loose envelope. It is expected to be small enough to have been ejected. It is expected to be darkened by radiation. It is expected to follow gravity. None of these expectations are precise. They are ranges. They leave room for variation. The purpose of defining typical interstellar visitors is not to predict exact properties, but to identify which properties would truly stand out. Typical visitors move on hyperbolic paths through the solar system, unaffected by planetary capture. Their velocities reflect galactic motion rather than solar system dynamics. Their brightness varies with distance and geometry, not with internal energy sources. Their behavior near the Sun depends on whether volatile materials remain accessible. Many are expected to be inert at solar distances where comets from the outer solar system become active. This is because interstellar objects may have lost surface volatiles long ago. These expectations are grounded in laboratory studies of ice sublimation radiation chemistry and thermal diffusion, as well as in observations of long-period comets that have spent extended time in cold storage. Typical interstellar visitors are also expected to be structurally resilient. Ejection from a planetary system is not gentle. It involves gravitational interactions that can impart high velocities and stresses. Objects that survive intact are those with sufficient cohesion. Very fragile aggregates are more likely to fragment during ejection or over long journeys. This introduces a selection effect. The population that reaches other systems is biased toward bodies that can endure. This does not make them unusual. It makes them representative of survivors. When observers consider 3I/Atlas in this context, they do not assume it represents all interstellar debris. They assume it represents debris that survived. This distinction matters. Typical does not mean average of all formed objects. It means average of those detected after filtering by survival and observability. Observability adds another layer. Detection depends on brightness distance and survey coverage. Dark, small objects are harder to see. Only those passing relatively close to the Sun and Earth, or those with favourable reflectivity, are detected. This further biases the sample. Typical detected interstellar visitors may not be typical of the unseen majority. This limitation is acknowledged at the outset. It tempers conclusions. Within these constraints, typical properties are described conservatively. Typical visitors do not show rapid changes in trajectory unexplained by gravity. Typical visitors do not emit significant light beyond reflected sunlight. Typical visitors do not display engineered symmetry or controlled motion. These statements are not claims about impossibility. They are summaries of observed and modelled behaviour. They define a working baseline. Any deviation must be evaluated against this baseline carefully with attention to measurement error and alternative explanations. For 3I/Atlas, early observations place it comfortably within many of these typical ranges. Its size estimates fall within expected bounds given brightness and distance. Its surface appears dark. Its motion is consistent with a gravitationally dominated trajectory. At this stage, there is no immediate departure from the established picture of interstellar visitors. This is important. The narrative does not begin with surprise. It begins with familiarity. By establishing what is common, the analysis creates space to later identify what is not. The inward movement of the exploration path remains gradual. The outer environment has been defined. The general class of objects has been outlined. Within that class, 3i/Atlas is introduced not as an exception but as a member. This membership is provisional. It will be tested as analysis proceeds. For now, the object sits quietly among expectations shaped by physics and limited observation. Typical interstellar visitors are diverse but bounded. They are products of known processes acting over long times. They are shaped by ejection radiation and survival. This framework holds. It provides the next inward step where detection circumstances and local measurements will be examined without altering the calm established here. The architecture of silence begins not with sound but with spacing. The narrator observes that 3i/Atlas does not announce itself loudly in the sky, the way sudden novae or violent gamma bursts do. Instead, it moves with a restraint that feels almost intentional, threading its way through regions of space where gravitational noise is low and observational clutter is minimal. In the cold outskirts beyond the familiar planets where sunlight thins and time stretches, motion becomes easier to read. Here trajectories speak more clearly than flashes. 3i/Atlas enters this quiet architecture as if it understands it, its path shaped not only by gravity, but by the absence of disturbance. Astronomers note that most interstellar objects arrive chaotically bearing the scars of turbulent origins, but this one does not. Its velocity is high, yet controlled, its angle shallow rather than steep. Its approach curiously well aligned with the plane in which our system already moves. The narrator lingers on this alignment, describing how coincidence in celestial mechanics is statistically common once or twice, but begins to feel unusual when compounded across multiple variables. Silence in this sense is not emptiness. It is structure, without ornament, order without announcement. The object's light curve shows minimal tumbling, suggesting a stability that contradicts the violent journeys expected between stars. Even its rotational period appears subdued, as if energy has been damped rather than excited. In laboratories on Earth, researchers simulate such damping and find it rarely survives long interstellar timescales unless continuously maintained. The narrator does not claim intent, only notes the improbability of preservation. As 3i/Atlas passes through regions populated by faint Kuiper belt bodies, its trajectory avoids close encounters that would be statistically likely given the density maps. It is as though the object threads between gravitational wells with practiced ease. The sky, usually a place of collisions and perturbations, allows this visitor to pass with almost ceremonial clearance. The narrator reflects that in human architecture, silence is engineered deliberately. Libraries, observatories, monasteries. Walls are thickened, corridors, bent surfaces softened, all to protect a fragile condition where subtle signals can exist. Space has no walls yet. Here is a corridor of calm, and 3i/Atlas follows it faithfully. Instruments listening for radio emission detect nothing anomalous, but the absence itself becomes data. No erratic outgassing, no asymmetric jets, no sudden changes in spin. Each expected noise source is checked, then quietly crossed out. The object behaves like a body that has already shed volatility elsewhere, or one that was never volatile to begin with. The narrator moves inward from motion to composition, describing spectroscopic readings that reveal surfaces aged by radiation, but not fractured by stress. Micropitting suggests long exposure without catastrophic impact. This again contradicts the usual interstellar narrative of survival by chance. Instead, survival here feels curated. The narrator allows the idea to hover gently, not as accusation but as curiosity. What survives silence best is not strength, but balance. As days pass, tracking arcs grow longer, prediction sharper. The object does not wander, its ephemeris tightens rather than spreads. Each update reduces uncertainty faster than models anticipate, because the object keeps doing exactly what the equations expect. There is comfort in this for the scientist, but also unease. Nature often resists perfect prediction. Chaos is its signature. Yet here the numbers settle early like a book that refuses to surprise beyond its opening chapters. The narrator describes a late-night observatory scene, red lights glowing faintly, screens filled with residual plots. Deviations are present, but small, smooth, almost musical in their periodicity. No jagged edges, no spikes. Just gentle oscillations consistent with distant, massive influences rather than nearby randomness. This leads the narrator to consider scale. Silence, too, has scale. A whisper is quiet because of proximity. Cosmic silence is quiet because of vastness. 3. I/Atlas exists comfortably in that vastness, neither shouting nor fading. It maintains a presence that can be tracked without demanding attention. In the deep past of astronomy, such behavior would have gone unnoticed, slipping through before instruments matured. Only now, with wide-field surveys and automated vigilance, does such quiet order become visible. The narrator suggests that perhaps the universe has always contained structures that rely on being overlooked, not hidden, just unassuming. The section closes by returning to architecture, describing how ancient builders aligned temples not for spectacle, but for endurance, choosing orientations that minimize stress across centuries. 3. I/Atlas, the narrator says, feels similarly oriented not toward us, not toward the sun, but toward longevity. It moves as if silence itself were a design constraint, a requirement rather than a byproduct. And in that silence, something profoundly organized continues its passage, indifferent to attention, yet perfectly legible to those patient enough to listen to what is not being said. When numbers begin to agree, opens with a quiet shift from observation to accounting. The narrator explains that once an object's path is established, astronomy becomes less about looking and more about counting, measuring, reconciling. 3. I/Atlas enters this numerical phase smoothly. Data streams from different observatories, optical infrared radar-assisted extrapolations begin to converge faster than expected. Normally independent measurements argue with each other. Small biases, atmospheric distortions, calibration errors all introduce friction. Here the disagreements are modest and short-lived. The numbers correct themselves as if guided toward consensus. The narrator lingers on this, emphasizing that agreement in science is rarely immediate. It is earned through resistance. Yet resistance seems unusually low. Orbital elements refine rapidly. Semi-major axis eccentricity inclination all settle into ranges that leave little room for surprise. The object's hyperbolic excess velocity confirms its interstellar origin beyond reasonable doubt, but its margin above escape velocity is narrow, precise, almost conservative. It arrives not as a reckless projectile, but as a traveller who expends only what is necessary. The narrator notes that energy efficiency is not a concept astronomers often attribute to natural wanderers, yet the mathematics here keep suggesting it. When models incorporate perturbations from Jupiter and Saturn, the predicted path barely wavers. The object's timing through nodal crossings avoids resonant kicks that typically scramble trajectories. Statistically, such avoidance can happen by chance, but the narrator reminds the listener that chance accumulates debt. Each unlikely alignment increases the cost of coincidence. As datasets lengthen, researchers begin running backward integrations, rewinding the orbit through time. Thousands, then millions of years unwind in simulation. Most interstellar objects blur into uncertainty quickly when traced backward, their origins dissolving into probabilistic fog. 3. I/Atlas resists this blur. Its past remains coherent longer than expected. Error envelopes widen but slowly smoothly maintaining shape instead of fracturing. The narrator describes this like ink spreading in water versus oil remaining intact. Both move, but one preserves boundaries. This coherence allows astronomers to tentatively identify regions of galactic space it may have traversed. Not a single star, not a home, just corridors, low-density lanes between spiral arm features regions where gravitational tides are gentle. Again, the theme repeats avoidance of turbulence. The narrator emphasizes that none of this violates physics. No laws are broken. Instead, laws are followed with an unusual degree of discipline. In conference rooms and quiet offices, scientists begin comparing this object to statistical ensembles rather than individual cases. Where does it fall on distributions of velocity, spin, reflectivity, often near the center, rarely at extremes? Outliers draw attention, but averages endure. 3. I/Atlas behaves like an average drawn from a population that has not yet been observed. The narrator lets this thought linger, careful not to suggest origin stories only populations implied by math. Spectral analysis adds another layer of numerical calm. Ratios of reflected wavelengths remain consistent across rotations, suggesting surface homogeneity at scales larger than typical rubble piles. This does not imply artificiality, the narrator cautions, but it does suggest formation or processing under stable conditions. Many asteroids are chaotic assemblies, records of collisions. This one reads more like a manufactured alloy not built but annealed by time. Temperatures inferred from thermal emission align neatly with predictions. No unexplained excess heat, no cold anomalies. The numbers behave. Even non-detections contribute. Upper limits on gas production constrain models, tightly ruling out volatile-rich scenarios early. The narrator notes how rarely science enjoys such clarity. Often uncertainty drags on for years. Here clarity arrives early, almost prematurely. This creates a strange emotional inversion. Instead of excitement building, it plateaus. With fewer mysteries to chase, attention shifts from discovery to interpretation. Why does this object fit so well? The narrator introduces the idea of overfitting gently a statistical trap where data appears too clean, prompting suspicion not of the data, but of the assumptions framing it. Researchers begin stress testing models, deliberately injecting noise, relaxing constraints, asking whether the agreement is an artifact of shared biases. Independent teams reprocess raw images, recalibrate photometry, adjust star catalogues. Results return essentially unchanged. Agreement persists. The narrator describes this as standing in a room where everyone independently hums the same note without coordination. It is not impossible, but it is unsettling. As weeks pass, prediction windows extend. Future positions are forecast with confidence unusual for a newcomer. Telescopes schedule observations months ahead, trusting the ephemeris. That trust is rewarded. The object arrives on time every time, crossing predicted coordinates within margins that shrink instead of grow. The narrator reflects on how prediction underpins all engineering. Bridges, clocks, spacecraft all depend on systems behaving as expected. When nature behaves this way, it feels momentarily cooperative. Yet astronomy has taught generations to expect indifference, not cooperation. The section deepens by examining mass estimates derived from non-gravitational forces, or rather their absence. Comets reveal themselves through tiny thrusts from outgassing. Here residual accelerations are negligible. This simplifies equations dramatically. Force equals gravity, nothing more. The narrator notes how elegant Newton's laws look when stripped of corrections. 3I/Atlas moves like a textbook example, rendered in real sky. Even relativistic adjustments are small, clean, easily accounted for. The universe for once is not improvising. As data quality improves, attention turns to error bars themselves. They are symmetric, well-behaved Gaussian. Few skewed tails, few surprises. Statisticians trust distributions like these. They signal that underlying processes are stable. The narrator muses that stability is often invisible until contrasted with chaos. We notice storms, not calm seas, yet here calm becomes the signal. The calm demands explanation not because it is impossible, but because it is persistent. Toward the end of the section, the narrator introduces a philosophical pause. Numbers agreeing does not mean meaning has been found. It means the universe is speaking in a language we already know. The discomfort arises not from misunderstanding, but from understanding too easily. When equations close neatly, curiosity does not end. It shifts inward. Are we asking the right questions? Are we mistaking familiarity for completeness? 3i/Atlas continues on its path indifferent to spreadsheets and plots. But behind the scenes, something subtle has changed. The scientists trust their calculations, yet feel watched by them as if the math itself is observing the observers. The section closes with a final image, a chalkboard erased clean, formulas rewritten carefully, no corrections needed. In a discipline accustomed to revisions, the absence of revision becomes the anomaly. And as the numbers continue to agree, the silence between them grows more pronounced, inviting attention not to what fluctuates, but to what remains unwavering. The narrative moves inward from the settled mathematics of trajectory toward the object itself, now treated less as a point and more as a body. Once position and motion stop arguing attention, naturally shifts to rotation, shape and balance. 3i/Atlas rotates steadily, its light curve repeating with a rhythm that is neither rapid nor sluggish. Brightness rises and falls in a pattern that suggests elongation, but not extreme distortion. Many small bodies tumble chaotically, their spins altered by past collisions or uneven heating. Here the rotation appears principal, meaning the object turns around a single dominant axis rather than wobbling through multiple modes. This simplifies interpretation. The narrator explains that principal rotation is often temporary in small bodies, damped over time by internal friction. To observe it implies either youth, unusual internal cohesion, or a long history of gentle conditions. The measured period remains stable across observing campaigns, drifting only within expected uncertainties. No sudden accelerations, no hints of torque from jets or fragment loss. The spin state behaves as if preserved. As telescopes sample different viewing geometries, the amplitude of the light curve changes predictably. This allows rough reconstruction of shape. Models converge on a modestly elongated form closer to a stretched ellipsoid than a shard or pancake. The narrator notes that earlier interstellar visitors prompted debates over exotic geometries. Here, geometry provokes little controversy. It fits comfortably among known asteroid shapes scaled to an interstellar context. Surface reflectivity reinforces this moderation. The albedo, a measure of how much light the surface reflects, falls in the middle of known ranges for dark carbon-rich bodies. It is neither glossy nor pitch black. Again, the average asserts itself. When infrared data is folded in size, estimates tighten. Diameter falls within a range large enough to avoid rapid thermal cycling, yet small enough to cool efficiently. This balance influences internal stress. Rocks expand and contract with temperature changes. Extreme cycles fracture bodies over time. Moderate cycles preserve them. The narrator lingers on this because preservation is emerging as a recurring theme. As rotation and size align, density becomes the next inward layer. Density cannot be measured directly, but it can be constrained. The absence of outgassing suggests a lack of large volatile reservoirs. The stability of rotation argues against a loose rubble pile that would shed material under centrifugal stress. Models favour a cohesive interior, perhaps a mixture of rock and refractory organics compacted but not metallic. The narrator stresses that none of this is definitive. It is a narrowing of possibilities, not a declaration. Still, the narrowing proceeds faster than usual. Polarization measurements subtle changes in light orientation. After reflection, add texture. They indicate a surface composed of fine grains rather than large exposed facets. Regolith, a blanket of dust, and Suisui fragments appears likely. Such blankets form through repeated micro-impacts over long timescales. Each grain is a record of patience. The narrator describes how interstellar space, though sparse, is not empty. Over millions of years, even rare impacts accumulate. A surface smoothed this way implies longevity. Thermal inertia measurements deepen the picture. The surface neither heats nor cools instantly. Heat penetrates slowly, suggesting a porous upper layer over a denser substrate. This stratification mirrors that of many asteroids shaped within planetary systems. It is familiar, almost comforting. The narrator acknowledges a subtle tension here. An interstellar origin might encourage expectations of strangeness. Instead, familiarity dominates. The inward journey continues to stress analysis. As the object rotates, tiny variations in brightness reveal surface heterogeneity, but these variations are muted. No stark contrast between hemispheres emerges. Many small bodies show scars, bright patches from fresh impacts. Here, weathering appears uniform. Space weathering, the gradual alteration of surfaces by radiation and micrometeoroids, tends to darken and redden materials over time. The spectral slope of 3I/Atlas aligns with an advanced stage of this process. Youth is unlikely. Age is implied. The narrator is careful to define age here not as time since formation, but time since last major resurfacing. This distinction matters. An object can be ancient yet recently disturbed. This one shows no sign of recent disturbance. Its surface tells a quiet story of exposure and endurance. As focus narrows further, internal structure is reconsidered. Without direct sampling, scientists infer interior properties indirectly. The absence of non-gravitational acceleration suggests mass is evenly distributed. A lopsided mass would interact differently with solar radiation pressure. Calculations show that even under maximum plausible radiation, forces deviations would be minimal only if mass is sufficient and geometry balanced. The narrator explains radiation pressure, briefly describing how light carries momentum. In small low-density objects, this momentum can alter motion measurably. That it does not here again points to solidity. The object behaves like a stone, not a sail. Discussions of composition inevitably brush against chemistry, but only lightly at this stage. Spectra lack strong absorption, features associated with exposed ice or fresh minerals. Instead, broad features consistent with complex carbon compounds dominate. Such compounds are common in the outer regions of planetary systems, where ultraviolet light and cold temperatures allow them to accumulate. The narrator notes that this chemistry does not require a specific birthplace. It requires time and distance from heat. Many systems provide both. As Section 5 deepens, the sense of inward movement becomes almost tactile. From path to spin to surface to interior, each layer reveals consistency. Not perfection, but coherence. The narrator avoids attributing intention. Physics alone is sufficient. Objects that survive long journeys tend to share traits. They are selected by environment, not design. Fragile bodies fragment. Volatile, rich bodies erode. What remains are those with properties that allow endurance. 3I/Atlas may simply be what survival looks like on interstellar scales. Near the end of the section, the narrator reflects on how this realization reframes expectations. Instead of asking why this object is so orderly, it may be more appropriate to ask why disorder would survive. The universe filters relentlessly. Only certain combinations persist. This thought does not conclude anything. It only narrows attention further inward. The object continues to rotate, presenting the same face to instruments again and again, unhurried, unchanged. Measurements repeat, confirming earlier results. Nothing new intrudes. In a field where novelty is prized, repetition becomes notable. The section closes with the narrator observing that rotation is time made visible. Each turn is a clock tick marking persistence. As 3i/Atlas turns, it carries its past forward intact, offering not surprises but continuity. And in that continuity another layer waits to be examined. Attention moves further inward from the body's rotation and surface toward the thin boundary where material meets energy. This region is not a place in space, but a process layer defined by how the object interacts with light, heat, and the surrounding medium. 3i/Atlas travels through interplanetary space without developing a visible coma or tail. For many small bodies, especially those rich in ice, proximity to a star awakens activity. Frozen gases sublimate, carrying dust outward, and altering both appearance and motion. Here, such behavior is absent. Sensitive surveys search for even the faintest halo of scattered light, and find none above detection limits. The narrator explains that detection limits are not absolute silence. They represent thresholds shaped by distance, background noise, and instrument sensitivity. Still within those limits, the object remains inert. This inertness constrains composition. Volatile ices, such as water carbon dioxide or carbon monoxide, must be scarce near the surface, buried deeply or absent altogether. Thermal models are applied. As sunlight reaches the surface, temperature rises according to distance and reflectivity. Calculations show that if common ices were present within a shallow layer, sublimation would be unavoidable. Gas would escape, pushing gently but persistently. No such push is measured. The narrator emphasizes that this is not an assumption, but a comparison between expected and observed behavior. Where expectation fails to appear, exclusion follows. The surface appears dominated by refractory materials, substances that remain solid at higher temperatures. These include silicates and complex carbon-rich compounds. The interaction with sunlight is steady and predictable. Energy absorbed during daylight is re-emitted as heat during rotation, producing a thermal signature that matches models of inert bodies. There is no excess emission, no cooling anomaly that would hint at hidden ice vents. The inward movement continues to how energy penetrates the surface. Heat does not stop at the outermost grains. It diffuses downward its depth, determined by thermal conductivity and rotation rate. Measurements suggest that daily temperature variations affect only a shallow layer. Beneath that, temperatures remain stable. This stability matters. It means that even if volatile materials exist deeper inside, they are insulated. The narrator clarifies that insulation here is passive, provided by porous regolith and low conductivity. Such structures are common among asteroids shaped by long exposure to vacuum. Again, the pattern aligns with endurance rather than activity. Solar radiation pressure is revisited with more nuance. Earlier, its negligible effect hinted at sufficient mass. Here, the narrator explores how surface texture modulates that force. Smooth reflective surfaces experience different pressure than rough absorptive ones. Polarimetric data suggests roughness at small scales. Photons scatter in many directions, cancelling out net thrust. This scattering further suppresses non-gravitational acceleration. The object does not behave like a sheet or foil. It behaves like gravel fused into a single form. As the process layer deepens, interaction with charged particles enters consideration. The solar wind, a stream of charged particles flowing outward from the star, can erode surfaces and implant ions. Over long time scales, this alters chemistry at the nanometer scale. Spectral reddening is one result. The narrator notes that the observed spectrum of 3/Atlas is consistent with prolonged irradiation. No fresh surfaces are exposed. No recent fracture or shedding event interrupts the weathered skin. The absence of change over time supports this view. Observations taken weeks apart show no measurable evolution in color or brightness beyond geometric effects. Stability persists. Dust is also absent. Many small bodies shed dust passively even without strong outgassing as micro-impacts loosen grains. Here any dust production is below detection. This could mean grains are bound tightly by cohesion or electrostatic forces. Laboratory experiments on regolith analogues show that fine grains can adhere under vacuum due to van der Waals forces. In low gravity, these forces matter. The narrator briefly explains cohesion, defining it as attraction between particles at small distances. In such environments, cohesion can rival gravity. This helps explain how surfaces remain intact despite weak gravitational binding. The inward path reaches interaction with the interstellar medium itself. Outside planetary systems, objects encounter sparse gas and dust. Collisions are rare but cumulative. Over millions of years, even low-density environments leave marks. The narrator describes how cosmic rays penetrate surfaces, altering molecular bonds. These rays are energetic particles accelerated by distant astrophysical events. Their penetration depth exceeds that of solar radiation, modifying chemistry below the immediate surface. The spectral signatures of complex organics can result from this processing. Again, nothing unusual is required. Time alone suffices. As 3I/Atlas enters the inner regions of a planetary system, the surrounding environment changes. Photon density increases. Particle flux rises, yet the object's response remains muted. There is no flare of activity, no delayed reaction. This suggests that the inward heat wave has not yet reached volatile-rich layers, if such layers exist at all. The narrator stresses caution. Absence of evidence is not evidence of absolute absence. Deep interiors remain inaccessible. Still, the consistency across multiple interaction channels narrows the range of plausible interiors. The object behaves as though its outer shell is thick, processed, and protective. The process layer also includes magnetism, or rather its lack. Some bodies with metallic content can interact weakly with magnetic fields. No such interaction is detected here. This places limits on metallic abundance. Iron-rich compositions would produce subtle but measurable effects. Their absence again points towards silicate and carbon-rich materials. The narrator maintains a steady tone, avoiding implication. Each constraint is presented as conditional cumulative. Together they form a coherent profile. As the section progresses, the narrator reflects on how these interactions serve as filters. Energy probes matter continuously. Light heat particles and radiation test surfaces without pause. Over long durations, only certain structures persist. The object seen now is the product of that testing. It is not pristine in the sense of untouched. It is pristine in the sense of equilibrium. Nothing is actively changing because change has already occurred to completion. The inward journey pauses at the threshold between surface processes and internal chemistry. What lies deeper is shielded, inferred only indirectly. The narrator does not cross that boundary yet. Instead, attention lingers on the quiet dialogue between the object and its environment, a dialogue consisting of exchange without reaction. 3I/Atlas absorbs energy, reflects light, endures particle impacts and responds with steadiness. This steadiness is not dramatic. It is measurable, and measurement repeated and consistent defines the character of this layer. The section ends with the object continuing along its path, interaction ongoing, but subdued, as if the environment speaks and the object listens without reply. The inward movement now reaches a domain defined not by composition alone, but by motion contained within the object itself. Rotation becomes the focus. Rotation is inferred, not seen directly through changes in brightness over time. As 3I/Atlas turns, different portions of its surface reflect sunlight toward observers. If the shape is irregular, or the surface uneven, brightness rises and falls in a repeating pattern. This pattern is called a light curve, a simple record of brightness versus time. The narrator explains that light curves are among the most informative tools available when objects remain unresolved points of light. For 3I/Atlas, the light curve is measured carefully over many nights, corrected for distance and viewing angle. The result shows variation, but the variation is modest and regular. There are no abrupt spikes or chaotic shifts. This regularity implies a stable rotation state. The period of rotation is estimated by matching repeating features in the data. While exact values remain uncertain due to limited viewing geometry, the range is constrained. The object does not spin unusually fast. It does not tumble in a complex way. Tumbling, also known as non-principal axis rotation, occurs when an object spins around more than one axis. Such behavior produces irregular light curves that change shape over time. No such evolution is observed here. The narrator notes that tumbling is common among small bodies that have experienced recent collisions or uneven outgassing. Its absence suggests long-term stability. Rotation stability carries implications inward. A stable spin means internal mass distribution is balanced. Large voids or asymmetries would shift the center of mass and induce wobble. Over time, internal friction dampens complex motion, but only if the structure allows it. The observed steadiness implies either a monolithic body or a rubble aggregate that has settled into equilibrium. The narrator defines a rubble aggregate as a collection of fragments held together by gravity and cohesion, rather than solid rock. Many asteroids fit this description. In such bodies, rotation rates are limited by structural strength. Spin too fast and material drifts outward. For 3I/Atlas, the inferred rotation lies safely below that threshold. No mass shedding is detected. No dust trail forms along the rotational plane. This reinforces the picture of a mechanically calm object. Light curve amplitude, the difference between maximum and minimum brightness, offers clues about shape. Large amplitudes indicate elongated forms. Small amplitudes suggest more spherical or uniformly reflective surfaces. The amplitude observed here is moderate. This points toward a shape that is neither extreme nor perfectly round. The narrator avoids imagery beyond what clarifies measurement. The shape is simply constrained, not visualized. Surface features also influence brightness. Albedo, the fraction of light reflected, varies with material. Patchy surfaces create additional modulation. Over repeated observations, the pattern remains consistent. This consistency implies that surface regions are stable and not evolving. No new patches appear. No resurfacing event alters reflectivity. The inward narrative pauses on the role of sunlight in modifying rotation. Solar radiation can change spin over time through a process known as the Yorp effect. This effect arises when uneven absorption and re-emission of heat produce tiny torques. Over long periods, these torques can accelerate or decelerate rotation. For small asteroids, Yorp can be significant. The narrator explains that detecting Yorp requires precise timing over many years. Current data for 3I/Atlas are insufficient for direct measurement. However, indirect limits can be placed. The absence of rapid spin or spin-up signatures suggests that either the object is large enough to damp the effect, or its surface geometry cancels it out. Both possibilities fit within known physics. No adjustment is required. The discussion moves inward to how rotation couples with internal strength. If the interior were loosely bound with minimal cohesion, even moderate rotation could induce reshaping. Over time, material would migrate toward the equator, altering shape and light curve. This phenomenon is observed in some asteroids which develop equatorial ridges. For 3I/Atlas, no such evolution is detected within observational limits. Again, time is a factor. The narrator clarifies that the observation window is short compared to the object's lifetime. Still, the lack of any sign of ongoing reshaping suggests that major redistribution is not occurring now. The inward focus continues toward energy dissipation. As the object rotates, internal friction converts mechanical energy into heat. In solid bodies, this dissipation is minimal. In aggregates, it can be higher, especially if components shift. The absence of tumbling implies that any past dissipation has already reduced complex motion to simple spin. This reduction requires time spent in relative isolation. The narrator emphasizes that interstellar space provides such isolation. Encounters are rare. Disturbances are infrequent. A body ejected long ago can settle into a quiet rotational state long before detection. Rotation also influences thermal behavior discussed earlier, as the object turns day and night alternate across its surface. Faster rotation smooths temperature differences. Slower rotation allows greater extremes. The measured thermal emission is consistent with moderate rotation supporting light curve interpretations. Independent lines of evidence align. The narrator presents this alignment without synthesis or conclusion. It is simply noted. The narrative moves further inward to angular momentum, a conserved quantity describing rotational motion. Angular momentum remains constant unless acted upon by external torques. The observed stability implies that external torques are weak. No jets of gas apply force. No close encounters perturb motion. This steadiness is consistent with an inert surface and solitary trajectory. The narrator again avoids implication. It is a description of conditions. The rotation axis orientation is poorly constrained, but some limits exist. Depending on how the axis tilts relative to the orbital plane, seasonal effects could occur. If one hemisphere faced the sun for extended periods, localized heating might induce asymmetry. No such asymmetry is seen. Brightness variations remain symmetric over time. This suggests that either the axis is not extremely tilted or the surface responds uniformly. Both scenarios remain possible. The inward exploration reaches the boundary between rotation and structure. At this boundary, questions arise about whether the object is a single coherent piece or a collection of fragments. Rotation alone cannot answer this definitively. It can only exclude extremes. Rapid spin excludes weak aggregates. Complex tumbling excludes highly damped interiors. 3I/Atlas sits between these extremes, consistent with many known small bodies. The narrator underscores that consistency does not equal classification. It simply narrows possibilities. The section slows as it approaches its end. The object continues rotating quietly, predictably, carrying its angular momentum unchanged. Each rotation presents the same face to observers at the same phase. Light rises and falls again and again without surprise. This repetition is data. It is also restraint. The inward journey pauses here at motion that reveals structure indirectly awaiting the next step toward what lies beneath the surface entirely. The inward progression now leaves rotation as a surface signal and moves into the domain where motion, heat, and structure intersect. This region concerns how the body responds internally to external forcing even when that forcing is weak. The focus is stability under stress. Stress here does not imply damage or strain visible from afar. It refers to the internal forces that arise as the object moves, rotates, and experiences subtle gradients in temperature and gravity. 3I/Atlas travels along its trajectory without showing signs of structural adjustment. Its path is smooth, its rotation steady, its brightness variations consistent. These observations suggest that internal stresses are either small or well accommodated by the body's makeup. The narrator explains that every rotating object experiences centrifugal force, a tendency for material to move outward from the axis of rotation. In rigid bodies, internal strength resists this force. In loosely bound aggregates, gravity and cohesion provide resistance. The balance between these forces defines structural limits. For 3I/Atlas, the inferred rotation rate is far below the level at which disruption would occur for even weakly bound material. This margin implies that internal stresses from rotation are minor. Thermal stress is also considered. As sunlight warms the surface, temperature differences develop between illuminated and shadowed regions. These differences can cause expansion and contraction. Over repeated cycles, such thermal cycling can fracture rock. On small bodies, this process contributes to regolith formation. The narrator notes that thermal stress depends on material properties such as thermal expansion, coefficient, and tensile strength. Observations of surface inertness and lack of fresh dust suggest that any fracturing is slow. Either the material resists cracking or the cracks that do form do not propagate enough to release particles. This again narrows material properties without specifying exact composition. The inward examination continues to tidal stress. As the object passes through the gravitational field of a star, different parts of the body experience slightly different gravitational pulls. These differences stretch the object minutely. Tidal forces increase with proximity. Calculations show that along the observed path, tidal stress remains negligible for an object of this size and distance. There is no expectation of tidal deformation, and none is observed. This absence aligns with prediction. The narrator emphasizes alignment, not surprise. The stability of shape inferred from light curves supports this. The internal response to impacts is also considered. Even in interplanetary space, micrometeoroids strike surfaces at high speed. Each impact transfers energy locally. In weak structures, impacts can trigger larger rearrangements. For strong or well-damped structures, energy dissipates quickly. The lack of observable dust or brightness change suggests that impacts do not cascade into larger events. The narrator explains that damping refers to the ability of a material to absorb and distribute energy without failing. Porous materials can be effective dampers as voids compress slightly and dissipate energy. This property is consistent with rubble aggregates, but also with fractured monolithic rock. Both remain viable. Attention moves inward to how internal temperature behaves over longer timescales. Beyond daily cycles, seasonal cycles occur as the object moves closer to or farther from the star. These cycles penetrate deeper. The depth reached by seasonal heat waves depends on thermal conductivity and period. Models indicate that for bodies with low conductivity, seasonal effects remain confined to a shallow shell. Deeper interiors stay cold and unchanged. This insulation preserves internal structure. If volatiles exist at depth, they remain locked away. The narrator reiterates that this is a conditional statement. The presence of volatiles is neither confirmed nor denied. Only their inactivity is established. The inward narrative approaches the question of internal layering. Some small bodies differentiate separating materials by density. Differentiation requires sufficient heat, often from radioactive decay early in formation. Interstellar objects could originate from varied environments. However, differentiation leaves signatures. It affects density distribution and rotational response. The observed stability does not require differentiation. It does not rule it out either, but the narrator notes that simpler structures suffice. The principle applied is adequacy, not preference. No additional complexity is introduced without necessity. The narrator then addresses bulk density. Density influences how an object responds to forces. It affects gravitational self-binding and resistance to deformation. Density can sometimes be inferred from non-gravitational accelerations or from binary dynamics. Neither is available here. However, indirect limits arise. The absence of significant radiation pressure effects implies a mass above a certain threshold for the observed size. Combined with size estimates from brightness and assumed reflectivity, a minimum density can be inferred. This minimum lies within the range of rocky bodies. Extremely low-density structures such as fluffy aggregates with large void fractions become less likely. Again, less likely does not mean excluded. The narrator carefully maintains uncertainty boundaries. The inward exploration continues toward internal cohesion. Cohesion refers to forces that hold grains together beyond gravity. On small bodies, cohesion can arise from electrostatic attraction or chemical bonding at contact points. Laboratory experiments show that fine powders in vacuum can exhibit surprising strength. This strength allows small bodies to maintain shape even with low gravity. The narrator explains that cohesion is scale-dependent. It matters more for small objects. For larger ones, gravity dominates. The size estimates for 3I/Atlas place it in a regime where both contribute. The observed behavior fits this mixed regime. Internal cohesion helps explain why no mass loss occurs even under thermal cycling. The inward narrative pauses on the concept of equilibrium. Equilibrium here means a state where internal forces balance external ones over long periods. It does not imply stasis. Microscale changes continue, but they do not accumulate into observable transformation. 3I/Atlas appears to be in such a state. Its structure absorbs stress without rearranging. This equilibrium likely developed over long durations in a quiet environment. Interstellar space provides such conditions. The narrator states this without implication of origin timing. Only environment is described. As the section advances, attention turns to how scientists test these inferences. Models are built using ranges of parameters. Simulations explore how different internal structures would respond under observed conditions. Many fail. They produce activity deformation or acceleration not seen. Others succeed. The survivors define the allowed space. This process is iterative and conservative. It reduces possibilities rather than selecting a favored answer. The narrator highlights that this narrowing is the goal. Not explanation but constraint. The inward journey slows as it approaches the boundary where structure gives way to composition at a deeper level. Section 8 ends with the object continuing its passage internally. Quiet externally measured its stability, not dramatic but persistent. Forces act upon it continuously, yet its response remains within expected bounds for a body that has already adjusted to them long ago. The next step inward will address what that stable structure is made of at a finer scale, but this section remains with how it holds together, not what it consists of. The inward path now shifts from how the body holds together to what its material likely consists of at the level of bulk substance, rather than surface appearance. Composition here is inferred and directly assembled from how light is reflected, how heat is emitted, and how the object responds to its environment. No samples exist. No close approach resolves detail. Everything rests on interaction between matter and energy, measured at a distance. 3I/Atlas reflects sunlight in a way that produces a spectrum, a distribution of brightness across wavelengths. This spectrum lacks sharp features associated with exposed crystalline ice. Instead, it shows a smooth, gently sloped profile. Such profiles are common among asteroids rich in silicates and carbon-bearing compounds. The narrator explains that silicates are minerals built around silicon and oxygen, common in rocky bodies throughout planetary systems. Carbon-bearing compounds include complex organic materials formed through long-term processing of simpler molecules. These materials tend to darken and redden surfaces over time. The observed reflectivity is low to moderate, consistent with such mixtures. There is no indication of highly reflective metal-rich surfaces nor of fresh frost. Thermal emission provides a second constraint. As the object absorbs sunlight, it re-emits energy at longer wavelengths. The temperature inferred from this emission matches expectations for a dark rocky surface at the observed distance. No excess cooling is detected that would indicate sublimating ice beneath the surface. The narrator clarifies that sublimation consumes heat, lowering surface temperature. Its absence reinforces earlier conclusions drawn from lack of activity. Composition must therefore be dominated by materials that remain solid at these temperatures. The inward analysis continues to density implications. While density is not directly measured, composition influences plausible density ranges. Silicate-rich bodies typically fall within a known interval. Carbon-rich materials can lower density slightly, but not to extremes unless large voids exist. Combining reflectivity, thermal behavior, and dynamical constraints, the allowed densities cluster around those of known asteroids rather than comets. The narrator stresses that this is classification by exclusion. It does not assign a precise label. It narrows similarity. The narrative moves inward to spectral uniformity. Observations taken at different rotational phases show little variation in spectral slope. This suggests that the surface composition is relatively homogeneous at large scales. There are no distinct regions of radically different material. This homogeneity could arise from mixing during formation, or from long-term surface processing that smooths differences. In interstellar space, exposure to cosmic radiation can gradually homogenize surface chemistry by breaking and reforming molecular bonds. Over long durations, initial diversity fades. The narrator presents this as a mechanism, not a certainty. The inward exploration addresses hydration signatures. Some asteroids show evidence of water bound within minerals rather than as ice. These hydrated minerals produce subtle features in spectra. For 3I/Atlas data quality limits sensitivity to such features. No strong hydration signal is detected. This does not exclude trace amounts. It suggests that if hydration exists, it is not dominant at the surface. Again, surface processing could mask underlying material. The narrator maintains the boundary between observation and inference. Composition is further constrained by color comparisons. Astronomers compare colors of distant objects using standardized filters. 3I/Atlas falls within the broad distribution of primitive asteroids. It does not stand apart. This is notable not because it is ordinary, but because it is interstellar. Despite originating outside the solar system, its surface resembles many bodies formed within it. The narrator avoids drawing implications. Similarity is described, not interpreted. The inward focus tightens to microscopic structure. At grain scales, composition influences how light scatters. Rough porous grains scatter differently than smooth ones. Polarimetric measurements suggest surfaces composed of fine grains rather than bare rock slabs. This supports the presence of regolith, a layer of loose material covering solid substrate. Regolith formation requires time and repeated small impacts or thermal cracking. Its presence indicates a long exposure history. This is consistent with earlier stability findings. The inward narrative then considers the possibility of metal content. Metallic iron or nickel would alter reflectivity and thermal properties. No such signatures dominate. This suggests that metal, if present, is mixed within silicates, rather than forming large exposed areas. Such mixing is common in undifferentiated bodies. Differentiation, where metals sink to form cores, requires early heating. The lack of evidence for differentiation aligns with a primitive composition. Primitive here means unchanged by extensive melting, not unprocessed by radiation. The narrator defines the term briefly, then returns to plain language. The inward movement approaches chemistry altered by radiation. Cosmic rays and ultraviolet photons can transform simple carbon compounds into more complex ones. Over time, these processes create dark, refractory materials. These materials resist sublimation and contribute to inert behavior. Laboratory simulations show that such irradiation products are spectrally bland, lacking sharp features. This matches observations. The narrator notes that irradiation acts from the outside inward, gradually building a protective mantle. This mantle can be tens of centimeters thick over millions of years. Beneath it, composition may differ. The inward journey stops at the mantle boundary without crossing it. Composition at depth remains unknown. The narrator emphasizes that observations probe only the outermost layers. Still, those layers govern interaction. They define how the object appears and behaves. The narrative continues to consider whether the object could be a fragment of a larger body. Fragmentation can expose fresh material, but over time that material weathers. The absence of fresh features suggests that if fragmentation occurred, it was not recent. Again, time emerges as a quiet factor. Composition observed now is the end state of long exposure. The inward focus briefly touches on isotopic composition, noting that it cannot be measured remotely. Isotopes could reveal formation environment, but they remain inaccessible. This limitation is stated plainly. The narrator does not speculate. The inward exploration consolidates constraints without summarizing. Each property limits the next. Reflectivity limits composition. Composition limits density. Density limits structure. Structure limits response. All remain consistent. Consistency does not imply completeness. It indicates that no contradiction has emerged. The section slows as it reaches its end. The object continues reflecting and emitting energy, according to simple physical laws. Its material makeup, at least at the surface, fits within known categories of rocky bodies shaped by time and radiation. Nothing observed requires exotic matter. Nothing observed reveals internal secrets beyond reach. The inward path pauses here at bulk composition, inferred through distance and restraint, ready to move deeper toward finer-scale physical behavior that remains just beyond direct measurement. The inward movement now leaves bulk composition and approaches the scale where material behavior depends on how individual grains and bonds respond to energy over time. This region concerns microphysical processes not directly observable, but constrained by everything measured so far. At this level, the question is not what materials exist, but how they behave when exposed to vacuum radiation and slow thermal cycling across immense durations. 3. I/Atlas presents a surface that behaves as if it has reached a mature state. Mature here does not imply age in years, but degree of processing. The narrator explains that surfaces in space evolve towards stability. Unstable compounds are removed first. Volatile substances escape. Fragile structures collapse or fracture. What remains is what can endure. The absence of activity suggests that this selection has already occurred. At the grain scale, this endurance is governed by bonding forces. Atoms bond into molecules, molecules into solids. In vacuum without atmospheric shielding, bonds are constantly challenged by energetic particles. Cosmic rays penetrate materials, breaking chemical bonds and creating defects. Over time, these defects can recombine into new structures. The result is a gradual transformation toward complex cross-linked compounds that resist further change. Laboratory studies of irradiated carbon-rich materials show this progression clearly. Surfaces darken, spectra smooth, reactivity declines. The narrator notes that such materials become chemically quiet. They still interact with energy, but they do not respond dramatically. This quiet behavior aligns with observations of 3I/Atlas. Thermal cycling continues to play a role at this scale. As temperature rises and falls, atoms vibrate more or less intensely. Repeated cycles can cause microcracks. However, once microcracks form, further propagation depends on stress concentration. In low-gravity environments, stresses remain small. Cracks can stabilize rather than grow. Fine dust produced early may settle into pores, cushioning further stress. Over time, the surface reaches a condition where additional cycling produces little change. The narrator emphasizes that this is a dynamic equilibrium, not a static freeze. Processes continue, but their net effect diminishes. The inward focus moves to porosity. Porosity describes how much empty space exists within a material. At small scales, porosity affects thermal conductivity, mechanical strength, and gas diffusion. High porosity lowers conductivity, insulating interiors. It also increases surface area, enhancing radiation processing. The inferred thermal behavior of 3I/Atlas suggests moderate to high porosity near the surface. Heat does not penetrate deeply. Energy is absorbed and re-emitted locally. This supports the idea of a regolith composed of loosely packed grains rather than solid rock. Such regolith can still be cohesive at small scales due to electrostatic and molecular forces. The narrator explains that in vacuum grains can cling together more effectively than intuition from Earth would suggest. The absence of atmosphere removes competing forces. The inward narrative then considers diffusion. If volatile molecules existed beneath the surface, they could migrate outward through pores. The rate of diffusion depends on pore size, temperature, and molecular mass. Models show that in cold porous materials, diffusion can be extremely slow. Volatiles may remain trapped indefinitely. This provides another explanation for inactivity without requiring complete depletion. The narrator carefully distinguishes possibility from evidence. Inactivity constrains behavior, not inventory. Attention moves inward to charge accumulation. Surfaces exposed to sunlight and plasma can accumulate electric charge. Photoelectric effects eject electrons while plasma deposits them. Charge imbalance can cause dust grains to levitate or migrate. On some bodies, this leads to dust transport. For 3I/Atlas, no evidence of dust motion is seen. This suggests that either charge effects are weak or grains are bound strongly enough to resist movement. Strong binding again points toward cohesive regolith. The narrator briefly defines photoelectric effect as emission of electrons when light strikes material, then returns to plain language. At the microscale, mineralogy also matters. Different minerals respond differently to radiation. Some amorphize, losing crystalline order. Others remain crystalline but accumulate defects. Spectral smoothness suggests a significant amorphous component. Amorphous materials lack long-range atomic order. They tend to produce featureless spectra. Such materials are common in space-weathered surfaces. The narrator notes that amorphization is not destruction. It is reorganization. The material remains solid, but its internal order changes. This change reduces spectral contrast and chemical reactivity. The inward journey continues toward timescale. All microphysical processes described act slowly. Millions of years may pass before significant alteration occurs. In interstellar space, exposure times can be long. Ejection from a parent system does not reset surface processing. It merely changes the radiation environment slightly. Cosmic rays remain ubiquitous. Over such timescales, surfaces converge towards similar states regardless of origin. This convergence explains why interstellar objects can resemble solar system bodies at the surface level. The narrator avoids drawing explanations beyond process description. The inward focus now approaches the interface between microphysics and chemistry. Chemical bonds at the surface determine how the object interacts with incoming energy. If bonds are strong and cross-linked energy is absorbed and dissipated as heat, without structural change. If bonds are weak, energy can break them, releasing material. The observed behavior of 3I/Atlas suggests strong, resilient bonding. This resilience does not require exotic chemistry. It arises naturally from prolonged exposure. The narrator emphasizes that this conclusion rests on cumulative evidence. No single observation proves it. Together they form a consistent picture. The inward narrative pauses briefly on uncertainty. At this scale, direct measurement is impossible. Models rely on laboratory analogues and simulations. These analogues are imperfect. They approximate conditions but cannot replicate millions of years precisely. Uncertainty remains. However, uncertainty is bounded. The range of plausible microphysical states is limited by observation. Exotic states that would produce observable effects are excluded. Ordinary states remain. The inward movement reaches the deepest level accessible without speculation. Below this lies internal chemistry, at depths unreachable by energy exchange during observation. That domain remains untouched. The narrator does not cross into it. Instead, attention lingers on the surface layer as a mediator. It is this layer that defines how the object presents itself. At the microscale, it has been sculpted by energy into stability. The object does not resist interaction. It absorbs it calmly. Light arrives, electrons move, bonds, vibrate heat, flows outward again. Nothing accumulates, nothing erupts. The section slows, deliberately reflecting the slow processes it describes. 3I/Atlas continues on its path, its surface quietly processing energy at atomic scales, unchanged in any way that instruments can detect. This quiet processing is not absence. It is balance achieved over time, maintained without effort and observable only through its lack of drama. The inward progression now approaches the deepest region that observation can still constrain without crossing into pure conjecture. This region concerns the internal state of matter beneath the processed surface, where temperature, pressure, and composition interact over long spans of time. It is not the core in a planetary sense, but the interior volume shielded from direct interaction with light and particles. What is known here arises from what does not happen. Heat from the surface diffuses inward slowly. Models show that for an object of this size, even extended exposure to a star does not significantly warm the interior beyond a shallow depth. Temperatures at depth remain close to the background conditions of space. Chemical reactions that require warmth do not proceed. Phase changes that depend on heating do not occur. The narrator explains that cold interiors preserve early conditions. Materials remain in the state they entered long ago. This preservation does not mean they are pristine. They may have been altered before ejection from their original system. It means only that since entering interstellar space, change has been minimal. Pressure inside such an object is low. Gravity is weak. Even at the center, pressure is far below levels required to compress materials into new phases. Rocks do not transform. Ices do not melt. Chemical gradients, if present, remain frozen in place. The narrator emphasizes that this low-pressure environment limits internal evolution. Whatever structure exists inside is a remnant of formation and early history, not of recent processing. The inward focus considers whether internal voids might exist. Porosity inferred near the surface could extend inward. If so, the interior would be a network of grains and cavities rather than a solid mass. Such structures can persist indefinitely under low stress. Alternatively, porosity may decrease with depth as overburden compacts material. Both configurations remain possible. The narrator avoids preference. Observations do not discriminate. What is constrained is stability. Any internal configuration must support the observed rotation without rearranging. It must also resist collapse under self-gravity. These requirements are mild, easily satisfied by many known materials. The inward narrative then addresses internal chemistry. At low temperatures, chemical reactions slow dramatically. Without liquid phases, reactions rely on solid-state diffusion, which is extremely slow. Over millions of years, some rearrangement may occur, but at rates too low to produce observable effects. The interior chemistry of 3I/Atlas is effectively locked. If volatile compounds exist at depth, they remain trapped. Diffusion through cold, compact material is inefficient. The narrator notes that this trapping does not imply abundance. It implies persistence if present. Attention moves inward to radiogenic heating. Some materials contain radioactive isotopes that release heat as they decay. In small bodies, this heating can be significant early on but diminishes over time as isotopes decay. Given the unknown age of the object, current radiogenic heating is likely negligible. Even if present, the heat produced would be insufficient to alter internal structure. The narrator states this cautiously. Without knowing initial isotope content, absolute statements are avoided. Still, constraints from size and inactivity limit the effect. The inward exploration considers internal layering. If the object formed in a protoplanetary disk, materials could have accreted in stages producing layers of differing composition. These layers would remain intact under low stress. No observational signature reveals or denies such layering. However, the lack of differentiation indicators suggests that any layering is subtle rather than extreme. The narrator clarifies that differentiation requires melting and separation by density. No evidence points to such processes. The interior is likely a mixture rather than a stratified structure. The inward focus then turns to fracture networks. Internal fractures could exist formed during early collisions or ejection events. These fractures could weaken structure, but only if they remain active. Under current conditions with low stress and low temperature, fractures would remain static. They would not propagate. They would not heal either. The interior would be mechanically quiet. This quietness aligns with the observed lack of rotational damping changes. The narrator explains that active internal friction would alter rotation over time. No such alteration is seen. The inward narrative addresses the possibility of trapped gases. If gases were present at formation, they could be trapped in pores or fractures. Over time, diffusion would release them unless barriers exist. Cold temperatures slow diffusion greatly. Trapped gases could persist, but without a pathway to the surface, they remain irrelevant to observed behavior. No outgassing occurs. This again constrains pathways rather than inventory. The narrator maintains this distinction. Attention shifts to magnetic properties at depth. Some minerals carry remnant magnetization recording ancient magnetic fields. Such magnetization does not affect external behavior unless interacting with strong fields. None are present. Internal magnetization remains observationally silent. The narrator includes this to illustrate limits of inference. Many properties exist but do not manifest. The inward path now reaches the conceptual boundary of inference. Beyond this point, statements would require assumptions not supported by data. The narrator stops deliberately. What can be said is that the interior of 3I/Atlas is cold, mechanically stable, and chemically inactive on observable timescales. These qualities are inferred from the absence of heat-driven change, structural rearrangement, or mass loss. They are negative constraints, but they are strong. The narrator emphasizes that science often advances by exclusion. By ruling out what cannot be happening, the remaining possibilities become clearer. The interior is not melting, it is not reacting, it is not venting, it is not collapsing, it persists. The inward journey lingers on time once more. Internal conditions change slowly. Millions of years may pass without measurable difference. The object carries its interior unchanged across vast distances. This persistence does not imply significance. It is simply a state. The narrator avoids attributing purpose. The section slows as it concludes. The interior remains unseen and largely unchanging, shielded by the surface layers already described. What remains accessible to study lies not deeper within but outward again, in how this interior history intersects with the object's journey through space. That intersection will be addressed next, but here the inward path ends at the deepest level that observation can reach without speculation. He drifts now into section 12, where the question is no longer how the object moves, but how the system around it reacts, because nothing that passes through the outer architecture of a planetary system does so alone. Here gravity is not a single force, but a conversation held among many bodies at once, each speaking softly yet persistently. Section 12 observes the way 3I/Atlas threads itself through this conversation, and how the surrounding system answers back in subtle, measurable ways. The narrator remains distant, present tense watching, as equations written decades ago are tested not by experiment but by arrival. The object does not announce itself. It simply enters a region where planets have rehearsed their motions for billions of years, and the rehearsal briefly adjusts. The Sun remains dominant, its mass still commanding the stage, but the planets, especially the giants, contribute their own quiet authority. Jupiter's gravity extends far beyond its visible form, a vast invisible well that has shaped the solar system since its youth. Saturn's influence overlaps in resonance and counterbalance. Together they form a kind of gate, not solid, but statistical one that most interstellar objects never pass through. The narrator notes that 3I/Atlas passes through this region without dramatic deflection, not slingshotting wildly, not fragmenting, not shedding obvious material. Its trajectory bends as all trajectories must, but only by the amount predicted if the mass, velocity and distance are all assumed to be unremarkable, and yet the path remains unsettlingly tidy. Simulations run backward and forward show that small changes in initial conditions should have produced larger deviations by this point. They do not. The object seems to cooperate with the solar system's gravitational architecture as if it has passed through similar architectures before. This is not evidence of intention, the narrator reminds, but it is evidence of experience. In astrophysics, experience is encoded in distribution. Objects that survive many passages through stellar systems tend to share certain traits: compactness, internal cohesion, and a lack of volatile surfaces that would erode under repeated heating. Section 12 lingers on this idea. If 3I/Atlas has indeed wandered for millions or billions of years, it has learned nothing consciously, but its current form is the residue of countless interactions. Weak structures are stripped away. Fragile configurations do not persist. What remains is efficient, not optimized for any purpose, but filtered by time. Observatories now watch for secondary effects. Tiny perturbations in asteroid belts, minute shifts in dust populations, changes so small they are barely separable from noise. Most of these signals, when they appear, resolve into known processes: radiation pressure, solar wind mutual collisions. But a few correlations resist easy dismissal. A cluster of long-period comets shows a marginal increase in activity shortly after the object's projected passage through the outer system. The increase is not statistically decisive, yet it aligns temporally in a way that draws quiet attention. The narrator does not claim causation. Instead, the script rests in the space where correlation invites patience. Gravity works slowly at these distances. A passing mass can seed instability that takes decades or centuries to unfold. Section 12 expands outward, considering how the solar system itself is not a static arrangement, but a metastable pattern, constantly adjusting, constantly on the edge of subtle rearrangement. In this view, 3I/Atlas is not an intruder, but a perturbation one among many that have shaped planetary systems across the galaxy. The difference is only that this one is observed in real time. Models of galactic dynamics suggest that stars exchange material more often than once believed. The boundary between systems is porous. Interstellar objects are messengers not because they carry messages, but because they are messages, physical records of conditions elsewhere. The narrator reflects on how Section 12 reframes the sense of isolation. The solar system is not a closed room, but a clearing in a forest with paths constantly crossing. Some paths are well trodden, others faint. 3I/Atlas follows a path that is faint but not unprecedented. What remains unusual is the clarity with which it can be tracked, and the cleanliness of its interaction. As it approaches perihelion, thermal models predict surface heating, insufficient to drive strong outgassing if the surface is depleted of volatiles. Observations confirm this restraint. No dramatic coma blooms, no tail announces itself across amateur telescopes. Instead, there is restraint again, a consistency that feels almost intentional to human intuition, though the narrator carefully strips that intuition of agency. nature often produces patterns that feel deliberate simply because disorder has already been removed. Section 12 turns inward again toward instrumentation. Doppler measurements refine velocity estimates to fractions of a meter per second. These refinements tighten the window of possible origins. Backtracing the orbit through the galactic potential suggests a broad region of the disk rather than a specific star. The path intersects no known stellar system at the right time and configuration. This absence becomes part of the data. It implies an ejection long ago from a system that may no longer exist in its original form. Stars migrate, clusters dissolve. The birthplace of 3I/Atlas may be scattered across light years, its parent star now anonymous. In this sense, the object is older than memory. Section 12 emphasizes that the solar system has likely hosted countless such visitors before unobserved their passages, leaving no legend, only incremental adjustments folded into the present configuration. What makes this moment different is not the visitor, but the observers. Humanity has built instruments sensitive enough to notice, patient enough to track, and cautious enough to hesitate before drawing conclusions. The narrator pauses on this humility. Science advances not by certainty but by constraint, by narrowing the range of what can be said without overstepping evidence. 3I/Atlas constrains models of interstellar debris of planetary system formation of galactic mixing. It suggests that solid bodies can survive long interstellar journeys intact, that ejection is common, and that capture, while rare, is not impossible. As the section nears its end, attention returns to the system's response over longer timescales. Even after the object departs, simulations predict faint ripples in orbital elements of distant objects, too small to attribute confidently at present in ensemble averages. These ripples remind the listener that every passage leaves a trace even if it is smeared across thousands of orbits and millions of years. Section 12 closes not with resolution but with continuity. The solar system absorbs the encounter as it has absorbed all others by adjusting infinitesimally and moving on. The narrator's voice remains calm, neutral, almost whispering, as if acknowledging that the true scale of the interaction is not dramatic but cumulative. 3I/Atlas continues on its way unchanged in any obvious sense, while the system it passed through carries forward a memory too small to notice directly yet real. In the quiet of space, memory does not announce itself, it accumulates. He moves now into section 13, where the focus shifts away from motion and into action, and settles instead on interpretation, because once the measurements are taken and the simulations converge, what remains is the human attempt to understand what the object represents. Section 13 is not about what 3I/Atlas does, but about what it forces observers to reconsider. The narrator remains steady, present tense, watching how data becomes narrative without ever becoming myth. In control rooms and quiet offices, scientists look at the same plots and feel a subtle unease, not fear, but a sense that a familiar framework has been gently stretched. For decades, interstellar objects existed as statistical expectations rather than concrete encounters. They were predicted by models of planetary formation and ejection, inferred from excess mass loss in young systems yet rarely observed directly. Now with 3I/Atlas, the abstraction gains weight. It is not large, not luminous, not spectacular, but it is undeniably here, and that presence alters the tone of discussion. The narrator notes how language changes first. Papers become more careful with qualifiers like rare and unusual. Conference talks add new slides, not dramatic ones, but cautious extensions of existing graphs. The object does not overturn theory, yet it presses gently against its edges. Section 13 lingers on this pressure. Scientific understanding does not usually collapse, it bends, accommodating new constraints. The arrival of 3I/Atlas reinforces the idea that planetary systems are efficient at discarding material. During formation, more mass is ejected than retained. What remains as planets is the minority outcome. The galaxy therefore should be filled with orphaned debris-silent travellers between stars. This idea is not new, but now it carries observational weight. The narrator reflects on how confirmation differs from prediction. A prediction can be elegant, convincing, even inevitable, yet it remains hypothetical until something like 3I/Atlas crosses the field of view. Then the prediction becomes a responsibility. Models must now explain not just that such objects exist, but why this one looks the way it does. Its apparent composure, its lack of volatile display, its smooth trajectory, all imply a history that is neither violent nor fragile. Section 13 considers the implications for planetary defense narratives. Popular imagination often frames interstellar visitors as threats or omens, yet the data insists on banality. 3. I/Atlas is not aimed. It is not accelerating anomalously. It carries no energy beyond what its mass and velocity imply. The solar system is not under siege. Instead, the object reframes danger as rarity rather than intent. Interstellar impacts are possible, but they are governed by probability, not purpose. This shift matters. It pulls discussion away from dramatization and back towards statistics. The narrator remains careful here, emphasizing how science resists storylines that place humanity at the center. The universe does not arrange encounters for significance. Significance is assigned afterward. Section 13 turns to comparison. Previous interstellar visitors, fewer and less well characterized, showed different traits. Some displayed unexpected acceleration due to outgassing. Others had ambiguous shapes or compositions. 3I/Atlas fits none of these curiosities neatly. It is not extreme enough to simplify classification. Instead, it suggests diversity. Interstellar objects are not a single class, but a population with internal variation, reflecting the countless environments from which they originate. This realization expands uncertainty rather than reducing it. If diversity is the rule, then each new detection adds complexity instead of closure. The narrator notes how this complexity is welcomed quietly. Scientists prefer puzzles that deepen rather than conclude. Section 13 also reflects on the observational threshold. Detection of 3I/Atlas is not inevitable. It is the result of recent improvements in survey cadence sensitivity and computational filtering. A decade earlier, it might have passed unnoticed, another silent crossing folded into the background. This raises an uncomfortable thought. How many have already passed? How many will pass before detection becomes routine? The narrator does not answer but allows the question to linger. Routine detection would transform interstellar objects from curiosities into datasets. Patterns would emerge. Origins might be grouped statistically rather than individually traced. 3I/Atlas then occupies a transitional moment. It is neither the first theoretical example nor part of a large observed sample. It stands in the narrow space where attention is still focused, where each parameter is scrutinized with care. Section 13 shifts again this time toward philosophy, though it never names it as such. There is a subtle change in how humanity perceives its environment. The solar system is no longer just a place where objects originate and remain. It is a corridor, a node in a larger circulation. This does not diminish its uniqueness, but it does contextualize it. The narrator speaks of perspective rather than importance. To know that material from distant systems can pass through unchanged and unremarked is to accept a certain humility. The boundaries that once felt absolute become permeable. Space is not empty between stars. It is threaded with trajectories. Section 13 observes how this awareness does not provoke panic or wonder in equal measure, but a quieter response normalization. The extraordinary becomes part of the expected background. This is how science absorbs novelty. What once startled becomes a line in a table, a term in an equation. Yet the narrator allows room for a softer reaction. Even normalized, the idea remains vast. A fragment formed around another star under another spectrum of light now passes briefly through a familiar sky. No exchange occurs, no message is delivered, and yet connection exists simply by co-presence. Section 13 emphasizes that this is not communion but adjacency. The universe does not speak, but it does overlap. As the section continues, attention turns to future interpretation. How will this object be referenced decades from now? Likely not by name, but as a data point. It will appear in review papers in cumulative plots of velocity distributions and size estimates. Its individuality will fade, replaced by its contribution to averages. This is not loss, the narrator suggests, but transformation. Individual events give way to structure. 3i/Atlas will help refine the statistical texture of the galaxy. The narrator's tone remains even, acknowledging that some listeners may resist this flattening. Humans prefer singular stories. Science prefers ensembles. Section 13 gently resolves this tension by noting that both can coexist. The singular matters in the moment of discovery. The ensemble matters in understanding. As the object recedes from peak attention, interpretation stabilizes. The most extreme hypotheses lose traction. What remains is a modest but persistent shift in confidence. Interstellar debris is real, survivable, and observable. The galaxy is not just a collection of isolated systems, but an exchange network operating over immense timescales. Section 13 closes with a quiet acknowledgement of scale. The passage of 3i/Atlas through human awareness is brief, measured in months or years. Its journey through space spans millions of years. The asymmetry is not tragic. It is simply factual. The narrator remains in the present tense, observing how understanding always lags behind reality. By the time something is noticed, it has already been happening for a very long time. Section 13 ends there, not with an answer, but with a recalibration, leaving the listener aware that knowledge has shifted slightly, almost imperceptibly, yet permanently. The narrator turns inward again, moving from interpretation toward material consequence. Because once an interstellar object is accepted as ordinary in origin and behavior, attention naturally narrows to what it is made of and how it persists. Section 14 focuses on substance rather than story. The object remains distant, but the analysis becomes intimate, concerned with surface's internal structure and endurance over time. Observations of 3i/Atlas provide only indirect clues. Light reflects off its exterior and returns altered, carrying information about texture and composition. The spectrum lacks strong features associated with exposed ice, suggesting a surface depleted of volatiles or sealed beneath a processed layer. This is consistent with long exposure to interstellar radiation. Over millions of years, cosmic rays and ultraviolet light modify the outermost material of small bodies, breaking molecular bonds and darkening surfaces. The narrator explains this briefly, noting that such processing creates a crust that can insulate what lies beneath. Whether ice exists below remains uncertain. What is known is that the surface behaves like aged material not freshly exposed. This implies duration. The object has travelled for a long time without catastrophic disruption. Section 14 remains with this idea of survival. Interstellar space is not empty, but it is sparse, and collisions are rare. The greater challenge is gradual erosion. Micrometeoroids, radiation, and thermal cycling act slowly but persistently. That 3i/Atlas remains coherent suggests mechanical strength. It is not a loose cloud of fragments. Its rotation inferred from subtle brightness changes appears stable. This stability constrains internal structure. A rubble pile held together weakly would be more susceptible to spin alteration and breakup. The narrator does not claim solidity, only resilience. Resilience implies either cohesive forces stronger than minimal gravity, or a configuration that distributes stress effectively. These are technical distinctions, but they matter. They inform how material aggregates behave when removed from their birthplace. Section 14 continues inward, considering temperature history. As the object approaches the Sun, its surface warms, yet no dramatic change is detected. There is no visible coma, no expanding envelope of gas or dust. This absence does not prove lack of volatiles, but it suggests that any volatile material is either deeply buried or exhausted. Thermal models show that repeated passages near stars could drive off surface ice long before the present encounter. The narrator notes that this implies prior stellar flybys. The object may not be on its first close approach to a star. Its history could include multiple systems, each contributing incremental change. This layered history is not recoverable in detail, but its effects are cumulative. Section 14 emphasizes accumulation over event. Material properties record time more reliably than trajectories. The surface of 3I/Atlas is an archive written in chemistry and texture. Observers read it imperfectly, but enough is legible to suggest age beyond any solar system timescale. The narrator remains careful, stating only that interstellar residence is long relative to planetary orbits. Attention then shifts to comparison with solar system bodies. Many asteroids show signs of space weathering, yet their environments differ. Solar radiation is directional and periodic. Interstellar radiation is isotropic and constant. This difference affects how surfaces evolve. The narrator explains that without a dominant heat source, temperature gradients are small. Expansion and contraction are muted. Cracking from thermal stress is less severe. This may contribute to longevity. 3I/Atlas experiences cold for most of its existence. Cold preserves structure even as radiation alters chemistry. Section 14 narrows further, approaching the scale of grains. Dust particles on the surface interact with light in ways that reveal size distribution. Observations suggest fine material rather than large exposed blocks. Fine material increases surface area and accelerates weathering, yet it also dampens thermal shock. The narrator notes this balance. Nothing here is extreme. The object appears moderate in all inferred properties. This moderation is itself informative. It suggests that extreme cases are not required to survive interstellar travel. Ordinary fragments suffice. Section 14 lingers on this point. If ordinary fragments can persist, then interstellar space is likely populated by countless similar bodies. They remain unseen not because they are rare, but because detection is difficult. The narrator does not quantify abundance, only notes that survival conditions are less restrictive than once assumed. As analysis continues, attention turns to mass loss. Even without visible activity, sublimation at a microscopic level may occur. Individual molecules escape without producing detectable clouds. Over long periods, this still removes material. The narrator explains that such loss is slow, measured over millions of years. It reshapes surfaces without dramatic signals. This gradualism characterizes Section 14. Nothing happens suddenly. Everything accumulates. The object that passes now is the result of innumerable small interactions. This perspective aligns with planetary science more broadly. Planets, moons, and debris evolve through steady processes punctuated occasionally by impacts. For 3I/Atlas impacts are unlikely. Steady processes dominate. Section 14 moves toward the innermost consideration of what this implies for sampling and future study. Direct sampling is not possible for this object, but its properties inform mission planning. If interstellar objects are structurally robust and chemically processed, then capturing or intercepting them requires precision rather than brute force. Their surfaces may not yield pristine material easily. The narrator avoids speculation about missions, focusing instead on inference. Understanding material state informs what questions can be answered remotely. It also sets limits. Some information is lost to time. Not every origin can be reconstructed. Section 14 accepts this constraint. Science advances by narrowing uncertainty, not eliminating it. As the section approaches its end, the narrator reflects on scale again, but now at the smallest level. Atoms altered by radiation still obey the same physics everywhere. The material of 3I/Atlas is not exotic. It is familiar matter arranged under different conditions. This familiarity reinforces continuity between systems. Different stars produce different histories, but the building blocks remain consistent. Section 14 concludes by noting that the object's endurance is not exceptional by cosmic standards. It is typical of matter that has had time to settle into stability. The listener is left with an image not of spectacle, but of persistence. The object continues its passage unchanged by observation, carrying within it the quiet record of environments long past. The narrator moves to the final inward layer where observation meets limit. This region is not a place in space or a material depth, but the boundary of what can be resolved. Section 15 concerns what remains inaccessible, even after careful measurement. The object continues along its path receding from the inner solar system, and with distance comes diminishing signal. Light grows weaker, angles change, and uncertainty expands. The narrator describes this transition calmly. All observation depends on proximity, and proximity is temporary. The data collected during the brief window of visibility form a finite set. Beyond that set, inference must stop. This is not failure, but definition. Science operates within constraints set by geometry, time, and instrumentation. For 3I/Atlas, those constraints are clear. It is small, fast, and distant. Instruments capture integrated properties rather than resolve detail. Section 15 stays with this idea of integration. Each measurement blends multiple factors into a single value. Brightness includes size, reflectivity, and orientation. Motion includes gravity, prior velocity, and measurement error. Disentangling these factors requires models. Models reduce complexity but introduce assumptions. The narrator explains this gently without judgment. Assumptions are necessary but bounded. They are tested against consistency, not certainty. Section 15 emphasizes consistency across independent observations. When separate instruments agree within expected limits, confidence increases. For 3I/Atlas, such agreement exists at a basic level. Trajectory, brightness, trend, and lack of activity align. Yet alignment does not reveal origin in detail. It only narrows categories. The object fits within interstellar debris, not within any known solar system population. Beyond that, classification remains broad. The narrator does not refine it further. The inner boundary is reached. Attention then shifts to time, another inward dimension. The passage through the solar system is brief compared to the object's lifetime. The narrator notes this asymmetry. Observers see a moment. The object embodies ages. This difference shapes interpretation. Data are weighted toward the present encounter, while history remains largely unrecorded. Even so, present behavior constrains past conditions. The narrator explains that current stability implies a past without severe disruption. Violent environments leave traces. The absence of such traces limits scenarios. This narrowing is quiet and incremental. Section 15 continues inward by considering uncertainty itself as a measurable quantity. Astronomers report ranges, not points. These ranges reflect both instrument limits and natural variability. For interstellar objects, ranges are wider. This does not weaken conclusions, it defines their resolution. The narrator states that recognizing uncertainty prevents overreach. Claims remain proportional to evidence. In the case of 3I/Atlas, evidence supports interstellar origin and non-active behavior. It does not support detailed reconstruction of formation site. that remains beyond reach. Section 15 accepts this boundary. The narrator then considers comparison again, but now at the level of methodology rather than objects. The same analytical tools used here apply to comets, asteroids, and distant minor planets. Differences lie in signal strength and duration. Interstellar objects compress observation into shorter intervals. This compression tests systems and procedures. The successful characterization of 3I/Atlas demonstrates that current methods are sufficient for basic classification. They're not sufficient for fine detail. Section 15 frames this as a statement of capacity, not aspiration. Capabilities exist at certain scales. Others await future development. The narrator avoids forward-looking speculation, remaining within present tense and presentability. As the object recedes, telescopes track it until background noise dominates. At that point, data acquisition ends. Analysis continues, but no new information enters. This separation between observation and interpretation marks the inner limit of the encounter. The narrator lingers here. Knowledge accumulates until flow stops. What remains is synthesis, comparison, and archiving. Data are stored alongside those from previous interstellar visitors. Patterns emerge only after multiple instances. With 2 objects observed, so far patterns are minimal. Section 15 does not extrapolate. It simply notes that sample size is small. Small samples constrain conclusions. This is a fundamental principle stated plainly. The narrator then turns inward one last time toward the role of absence. The absence of activity, of dramatic change of anomaly beyond motion, is itself information. Absence rules out certain processes. It does not confirm others. For 3I/Atlas, absence suggests maturity and depletion. It also suggests that interstellar space favours survival of quiet objects. Loud ones announce themselves briefly and fade. Quiet ones persist. This observation is descriptive, not interpretive. The narrator does not attach meaning. Section 15 approaches closure by returning to the immediate present. The object is farther now, colder, less illuminated. Its influence on the solar system is negligible. Gravitational effects are localized and transient. No lasting alteration occurs. The passage is clean. This lack of consequence is noted without emphasis. Many events in space occur without aftermath. They are passages, not interactions. Section 15 rests here. The inward path reaches stillness. Observation has done what it can. The object continues beyond reach, carrying its material record unchanged by attention. The narrator remains with this continuity. Nothing is concluded. Nothing is resolved. The account simply ends where information ends.